So hello, welcome back. This is part 2 of my presentation on a compactness theorem in the moduli space of singular constant Q-curvature metrics. And in this presentation, in this part of the presentation, I will describe some of the tools we use in a proof. So the tools I'm going to talk about are, first, I will discuss the Delaney metrics. I will give a brief discussion of asymptotics. And so these are asymptotics of a singular solution near a point singularity. And finally, I will discuss the Pohozaev invariance. Okay, so first we're going to talk about the Delaney metrics. These are all of the complete constant Q curvature metrics on a sphere with two punctures, which are conformal to the round metric. And so I can use a conformal transformation to make my puncture points antipodal, and then I can transfer everything to Euclidean space using stereographic projection. After I do that, I obtain a function on Rn minus the origin, which satisfies this PDE. The bi-Laplacian of U is a dimensional constant times U to the n plus 4 over n minus 4. And C.S. Lin proved in the late 1990s that any function satisfying this equation is going to be rotationally invariant. So it turns out to be easier to classify these solutions once we do a cylindrical change of variables. And this is, we do this by letting t be minus the log of length x, and theta is x over length x, and v is now defined by this formula. So I have a prefactor, an exponential prefactor, but then essentially v of t and theta is u of e to the t minus times e to the minus t times theta. And once I do that, the new function satisfies a nice differential equation. So I have my Paneitz operator over the cylindrical metric, which is down here. It's very similar to the original Paneitz operator. You can think of it in Euclidean space. You think of this as just the Paneitz operator expressed in cylindrical coordinates. You see it's another fourth order elliptic operator, and it has some second order divergence terms. It has a constant term. But anyways, the new PDE looks like the cylindrical Paneitz operator applied to V is a dimensional constant times V to the n plus 4 over n minus 4. But I know that I only need to look for ODE solutions, and this means the all of these terms in my Paneitz operator with angular derivatives vanish. And this reduces me to looking for solutions to this ODE. It's a fourth order ODE. I have a fourth order term, I have a second order term, and I have two zeroth order terms, a linear and a nonlinear zeroth order term. There are two solutions we can find very quickly. The first one we already know, which is the spherical solution. If I apply my cylindrical change of coordinates to the spherical solution, I obtain this what I'm calling V sphere, which is cosh to the power 4 minus n over 2. And if I look for constant solutions to this ODE, I find this dimensional constant. It turns out that this epsilon n is between 0 and 1. It's also fairly straightforward to show that the ODE I have here, this ODE has a Hamiltonian energy. So what does that mean? That means that this H bar evaluated on any solution of this ODE is constant. And you can verify that by just taking a derivative of this right-hand side here, and you'll obtain V dot times the ODE, essentially. It is also a very straightforward computation to show that the spherical solution has Hamiltonian energy 0, while the cylindrical solution has a negative Hamiltonian energy. The kind of amazing thing about this setup is that even though we have a fourth order ODE, it behaves qualitatively like a second order ODE. So what do I mean when I say that? I mean that the solutions to this fourth order ODE are actually uniquely determined by only 2 initial conditions rather than 4. So you'd expect 4 initial conditions because you have a fourth order ODE, but in fact, you only need 2 initial conditions, say V of 0 and V dot of 0. And furthermore, one can show that these solutions are energy ordered. And this is the same as saying that if the Hamiltonian energy of V1 is less than the Hamiltonian energy of V2, then this minimum value of V1 is greater than the minimum value of V2. So you can think of trying to translate all of your solutions such that they achieve a minimum value at t is equal to 0, and then you essentially have all of your solutions determined by one parameter, that value at 0. And this parameter, the Hamiltonian energy of all my solutions is monotone in this parameter. That's what we have. And I'll also remark here that because this cylindrical neck size, this epsilon n, is the largest possible minimum value, we know that the Hamiltonian energy of all of my solutions is greater than or equal to the Hamiltonian energy of this cylindrical solution. Okay, so the Freck-Koenig classification follows from their proof that any global positive solution of my ODE must in fact remain bounded. So this means that I can use my energy, my Hamiltonian energy, to describe all of these solutions, and I only need my 2 initial conditions. So again, I can use my I know that all of these global solutions essentially behave like solutions to second order ODEs. And what does this tell you? This tells you that all of these solutions are in fact nice bounded periodic functions. They're uniquely determined by the minimum value over a period. Equivalently, they're uniquely determined by their Hamiltonian energy. So we're going to call the solution V epsilon that obtains its minimum at t is equal to 0, minimum value of epsilon at t is equal to 0. We're going to call that the Delaney solution with neck size epsilon. These solutions, the solution V epsilon has some period t epsilon. And it's also possible to show that the period is monotone with epsilon. And that when epsilon goes to 0, the period goes to +infinity. if I reverse my cylindrical transformation, I now obtain a solution in the punctured Euclidean space minus the origin, and it's obtained by and the formula for this solution on Rn minus the origin is u epsilon of x is length of x to the power 4 minus n over 2 v epsilon of minus log f, length of x. So here I've drawn some typical profiles. In green, we see the profile of the spherical solution. This is just cosh to a negative power, and we see that it starts with a height of 1 at t is equal to 0, and then decays down to 0. The cylindrical solution is constant. This is the black horizontal line. In between, I have some nice periodic functions, this red curve and the blue curve, and we see that when the neck size is smaller, the red curve has a smaller neck size, a smaller minimum value, and it also has a longer period. Here we have a plot of some of the level curves of the Hamiltonian energy in the VV dot phase plane. We see that the this curve here, this green curve here corresponds to the spherical solution, and this stationary point here, you should think of this stationary point as the bottom of an energy well, and this corresponds to the cylindrical solution. For all of the energy levels between the cylindrical energy and the spherical energy, which is 0, for all of these in-between levels, the corresponding solution curve in phase space is a closed bounded curve like this. And these closed bounded curves are exactly the level sets of my Hamiltonian energy. So I want to summarize some of the key features of the Delaney solutions. For each epsilon between 0 and this maximal neck size epsilon n, there exists a unique Delaney solution which realizes its minimum value of epsilon at t is equal to 0. Each of these Delaney solutions is a positive periodic function. And this is the complete list of all of my two-ended solutions. These are all of the solutions to my original PDE on all of R cross Sn minus 1, equivalently on all of Rn minus the origin. These Delaney solutions are indexed by the Hamiltonian energy. For each epsilon between 0 and epsilon n, this Hamiltonian energy is strictly negative. And when epsilon 1 is greater than epsilon 2, if and only if the Hamiltonian energy of V epsilon 1 is less than the Hamiltonian energy of V epsilon 2. And finally, when epsilon goes down to 0, we know that the period goes to infinity. And when I translate the Delaney solutions appropriately, I find the spherical solution. Okay, so I want to describe the asymptotics briefly. So the Delaney metrics are important examples. In addition to being these only two-ended solutions, they also describe the asymptotics of a constant Q curvature metric with an isolated singularity. So the first result in this was a theorem about 1.5 years ago by Jin and Sheng. They proved that if I have a function in a punctured ball, which is positive, is superharmonic, and satisfies Laplacian squared. The bi-Laplacian of u is this dimensional constant times u to the n plus 4 over n minus 4. Then I have an expansion that u is this power of x times a Delaney solution plus some remainder term, and this remainder term is appropriately small. So what does this say? This says that near any puncture point, the solution will look on a very small scale like a Delaney metric. One can actually refine this asymptotic expansion and essentially obtain the next order term in the Taylor expansion. So this is we don't need the refined asymptotics for our purposes in this paper, but I'll state them. In cylindrical coordinates, they're a little bit easier to state in cylindrical coordinates, but of course there's an equivalent statement in Euclidean coordinates. So what does this theorem say? It says that so again I have my function from say 0 cross infinity to 0 to infinity crossed Sn minus 1. It's a positive function. It satisfies my PDE, which is this PDE. The cylindrical Paneitz applied to V is this dimensional constant times V to the n plus 4 over n minus 4, plus an auxiliary condition, which is equivalent to saying that the Laplacian minus the Laplacian of u is greater than 0. Then I have an expansion, which looks like v of t of theta is a Delaney solution plus a correction term, which decays like e to the minus t. And this correction term has a part which looks like v epsilon dot and another part which looks like v epsilon. And then finally, I have a remainder term which decays like e to the minus beta t for some beta strictly greater than 1. Okay. As a consequence of these asymptotic expansions, we can assign some asymptotic data to each metric in the unmarked moduli space. So how do we do this? The first piece of this asymptotic data is obviously just the choice of the punctures, P1 through PK. So I can describe, first of all, at which points do these punctures take place. Next, for each of the punctures, I can describe the Delaney asymptote, the epsilon 1 through epsilon k, and finally, recalling that in my next order term for the refined asymptotics, I have in this term that decays like e to the minus t, I have the inner product of some fixed direction vector A with theta. I can associate a direction vector A1, A2, and so on with each puncture point. So this gives me a map from the unmarked moduli space to the k-fold product of the n sphere with a half open interval with Euclidean space of dimension n. And it's still open how well this asymptotes map describes the moduli space. So for instance, near certain points, this asymptotic data should parameterize the moduli space, but it is also probably not true that one can associate a point in moduli space to any choice of parameters listed here. Okay, finally, in the last part of part 2 of this presentation, we're going to describe the Pohozaev invariants. So the Pohozaev invariants all fit into a much larger principle, which is in physics usually called Newton's principle. And it says that if a variational problem has any symmetry attached to it, then any extrema or critical points associated to my variational problem will have conserved quantities associated to those symmetries. So in our setting, the variational problem, the functional that we're minimizing is this total Q curvature integral. So it's given by the ratio. If I choose a metric G in a conformal class G naught, I can write down this functional, which is I take the integral of the Q curvature of G and I divide it by the volume of M with respect to G to this certain power. And the reason I have to look at this ratio and I have to have this particular value of the volume down here is I want to have a ratio which is scale invariant. In fact, this whole ratio is invariant under the action of the conformal group, if there are any conformal transformations. But the important thing is that I need to have volume to this particular power in the denominator here, because otherwise I don't have any sort of reasonable variational problem. I can scale my metric by a constant and make the functional go to plus infinity or 0. But if I look at this scaling invariant ratio, then I get something that's reasonable to look at. So in our setting, this is the functional, and the symmetry group is the conformal group of the sphere, the group of conformal transformations of the sphere. So you have to be a little bit careful when you're defining this, when you're setting up this variational problem. So we won't need to go into all the details here. It's fairly standard. If you want to define this Pohozaev invariant in full generality, we don't need the full Pohozaev invariant for our purposes. So we're really we'll really only discuss part of it. But if you want to describe what this is in full generality, it would be a certain cohomology class taking values in the dual to the Lie algebra of the conformal killing fields. So how do I describe that? Well, if I want to describe a cohomology class, I need to say how that cohomology class acts on an element of homology. And then if I say that this cohomology class takes values in the dual to the Lie algebra I have to say how that dual element acts on a Lie algebra element, how that acts on how this dual Lie algebra element acts on a conformal killing field. And this action is given by an integral over my homology class of a certain 2 tensor applied to X and a unit normal. Okay, so this is all something that will appear in much more detail in all generality, and something that is work in progress. The Hamiltonian energy, so we only need to describe the radial part of this full Pohozaev invariant. The Hamiltonian energy we describe in, we defined for the Delaney solutions, this actually extends to a Hamiltonian energy for all my solutions, regardless of whether or not they are functions of t alone or functions of both t and theta. So the formula for this Hamiltonian energy looks a little bit complicated. Is basically the Hamiltonian energy I had before for the ODE, but now because I have angular derivatives, I have to add in some angular terms. It looks a little bit strange that I've decomposed my Hamiltonian energy into what I've called the cylindrical part and this nonlinear part here. But this will turn out to be a little bit convenient for the final part of the presentation. Okay, if I integrate by parts, I find that this integral of the Hamiltonian energy over a slice, a constant t slice, actually does not depend on t at all. And furthermore, if my function v satisfies the equation cylindrical Paneitz applied to v is equal to a constant multiple of v to the power n plus 4 over n minus 4, then this particular modified Hamiltonian energy here is independent of t. Does not depend on t at all. Okay, so now we're able to say what the radial Pohozaev invariant of a metric at a puncture point is. I start with my metric g, which is conformally flat, so g is equal to u to the power 4 over n minus 4 times the round metric. This is a complete constant scalar curvature metric on the sphere minus these punctures P1 through PK. And for each of these puncture points, I pick a ball small enough such that the PJ is the only puncture point inside that ball. And inside this punctured ball, I do my cylindrical change of coordinates, and now I obtain a function Vj, which satisfies my cylindrical Q-curvature equation. And finally, I can describe the radial Pohozaev invariant of the metric G evaluated at the point Pj is equal to this integral over a constant t slice of my Hamiltonian energy of Vj. And because this Hamiltonian energy, the integral of this Hamiltonian energy does not depend on t at all, I see that it doesn't matter which t I choose to define this integral, so long as I choose some t such that the integral is well defined. Furthermore, I can use my asymptotic expansion that we've just described a couple slides ago I know that my Vj is actually some Delaney solution V epsilon j plus a term that decays like e to the minus t. And this tells me then that my radial Pohozaev invariant of my metric G at the point Pj is equal to the Hamiltonian energy of V epsilon j times the volume of an n-1 sphere. In particular, each of these radial Pohozaev invariants must be negative. So the by the previous discussion of the Delaney metrics, we know that in fact the radial Pohozaev invariant at each puncture point will uniquely determine the next size epsilon j at that puncture point. So in particular, bounding all of these asymptotic next sizes away from zero is equivalent to bounding all of the radial Pohozaev invariants away from zero. And we're going to use this equivalence later on in the proof of the theorem. So this is sort of the key point about the Pohozaev invariance, is that one of the key points about the Pohozaev invariant is that controlling these Pohozaev invariants is the same thing as controlling the next sizes. So in the final part of the presentation, we will sketch a proof of the main theorem. And so the statement of the main theorem is that if a subset in the unmarked moduli space satisfies that all of the spherical distances between punctures is bounded away from zero and all of the asymptotic next sizes remain bounded away from zero, then this subset is sequentially compact. And how do we prove this? There are really two steps. So the first step is that we prove an a priori estimate for all of these functions, which are the conformal factors. And the a priori estimates allow us to extract a limit, which is a candidate for the thing we'd want to converge to. So I can extract a limit function. It would remain now to show that this limit function you obtain is strictly positive. It doesn't have any points at which is zero, and this is where using the next sizes bounded away from zero becomes important. So we will discuss the sketch of this proof in the final part of this presentation. Thank you for listening, and we will see more on this soon.